So, now let us go ahead and develop the current voltage characteristics. The electrostatics of the Mosfet has already been in some sense covered when we discussed the MOS capacitor. Okay. So, what we will do now is look at the current voltage characteristics of the Mosfet. Of course, the electrostatics are, in the MOS capacitor, the electrostatics did not include the influence of the source and drain, but that is quite easy to include, and it is just a matter of changing the potential of the semiconductor. What we will look at now is, once you have created the inversion channel, what is the current, what is the current voltage characteristics, in particular what current am I looking for. We are not interested in the gate current, because ideally there should be no gate current. Okay, so, we are not interested in the gate current, Ig should be 0, and that is the whole point of the Mosfet or the field effect device. If Ig is 0, it is because you have an insulator there, and therefore, the input impedance is infinite. Okay, so, ideally that is what we are trying to achieve. We are trying to achieve a variable resistor with an infinite input impedance, variable channel resistance, but the gate input impedance is infinite. Okay, so, that is the ideal dream. Now, what we are trying to look at is this current. Okay, what is the drain to source current? Okay. So, if you are talking about a P channel device, if you are talking about an N channel device or an NMOS, you have a P type semiconductor and you have electrons there, and the electrons and the drain is going to be at a higher potential. So, let us say at 2 volts, the source is with respect to the source, and therefore, the electric field is in this direction, and therefore, the electrons will all come in from the source and they will all migrate to the drain, which means the current is going to be in this direction. You are going to have a I from the drain to the source, and we want to find out what is the drain to source current. All right. So, how do we go about this? And before we continue, this is equally true for an N channel device. Okay. So, for a P channel device. So, if it is a P channel device, you will have, if it is a PMOS, you will have your N type semiconductor, and you will have holes at the interface after inversion, and these holes, the source will be at a higher potential with respect to the drain. So, for example, let us say let's look at this as being 2 volts and that is ground. So, the holes will be entering from the source, they will migrate to the drain, and the direction of the movement of the holes will be this, and the current direction will be this. Okay. So, you will have an IDS that is negative, VDS that is negative, etc., etc. Okay. But the idea or the physics behind deriving the current voltage characteristics is the same. Now, since we have discussed a P type body, and since we have discussed a P type MOS capacitor, let us just stick with a P type semiconductor and an NMOS device or an electron channel being formed at the interface during inversion. So, how does this device work? Now, when VGS is not 0, when VGS is equal to is less than VT, there is no channel, okay, technically, because it is all depleted. But once VGS becomes greater than the threshold voltage, you now have inversion and you have a channel that forms. Okay. So, the channel is indicated in this picture, and it is indicated as this blue region. So, that is the electron channel from source to drain. If I were to take a voltmeter and head from the source to the drain, okay, or from the source to the drain, and I were to measure the potential of the channel at every point, okay, what is the potential? So, let us call that potential as Vc, which is the channel potential. So, let us give a name for this particular potential, which is Vc, okay, which is the channel potential, which means we have created an N channel, we have created an electron interface. Okay. So, you have electrons here, but then these electrons, we are going to go around with the voltmeter and measure the potential of this channel of electrons from the source to the drain, and we are going to measure that potential with respect to the source, okay, and we are going to call that potential Vc. What is that potential? So, right here so you can think of this whole path of electrons as a long resistor, right, it has got some resistance. So, right at this edge what is the potential? It is 0, it is the same as the source, okay. The potential here is Vs and this point is Vs. So, Vc is basically the potential that you measure minus, it is all with respect to the source, and therefore, the Vc is 0, okay. So, let us give this a direction. So, we are calling this the y direction, and therefore, at y equal to 0 Vc is 0. Now, let us move ahead. Now, at some other point the potential difference between these two will be Vc of y, okay, because it is varying with y, and as you go to the drain, as you approach the drain side, the potential here is going to be the same as the drain potential, and therefore, at y equal to L, which is the channel length, Vc is going to take a value of Vds, which is the drain to source voltage, because all these potentials are measured with respect to the source. So, you are going to keep one probe there, another probe here, and this potential difference is Vds, all right. So, that is your channel potential. So, in order to imagine, in order to derive this current, we see that it is the Vds that is providing the electric field, and these are in response to the electric field, these electrons are going to drift through from the source to the drain. So, what is the drift current density? So, that is J, which is the drift current density, the current per unit area. It is Q N Vd, okay, where Vd is the drift velocity of the electrons, N is the number of electrons per unit volume, and Q is basically your 1.6 into 10 power minus 19 coulombs. So, that is your drift current density. Now, what is the total current? It is the current density times the area of cross section, and in order to identify the area of cross section, what we are going to do is we are going to define this electron channel as having some thickness h, okay. Now, that is an odd definition, because all of you are already familiar with the fact that the electrons are all wave particles. So, to define them as having a certain thickness h is odd, but we are going to go ahead and treat these electrons as particles and define the sheet as having a thickness h. And this sheet of electrons has got a width which is equal to the channel width of your device, okay. You got this sheet charge which is all migrating towards the from the source to the drain, it is all migrating from the source to the drain. So, what is the total current? The total current, which is your IDS, is basically this current density into the area of cross section, and what is the area of cross section? It is basically W into H, where W is the channel width and H is your thickness of this electron sheet, okay. So, we can write this little equation down, which is IDS by WH is the current density, and that is equal to Qn into the drift velocity. But what is drift velocity? The drift velocity is nothing but the mobility times the electric field. So, we can rewrite that equation as Qn mu into the electric field, where mu is the mobility of the electrons. And furthermore, what is the electric field? So, if I were to now take a little section, we already know what the channel potential is, right. So, if I were to take a little section, let us take a small section here. So, that is our y direction, and let us say the section has got a length dy, okay, and we say that the voltage drop across the section is basically dVc, that is a delta of the channel potential. So, you have a section of length dy and the voltage drop across the section is basically dVc. So, what is the electric field across the section? It is dVc by dy. So, we replace this electric field term by dVc by dy. So, you have Q n mu dVc by dy as your current density, and that is equal to your IDS by WH. Okay. Now, in order to identify IDS, we need to now calculate what is N. Okay. So, how do we find out what is N? N is the number of electrons per unit volume sitting near the channel. So, if you recollect your MOS capacitor, okay, we had already identified. So, if you remember the MOS capacitor, let us just go back a little bit. So, we had the MOS capacitor, which was a metal insulator semiconductor structure, and we had in inversion we had an electron sheet, and we had defined that inversion charge is Q I and V, that was the inversion charge per unit area. So, the MOS capacitor had a gate voltage Vg, it had and this also with respect to this grounded back contact, okay, and it had generated this inversion layer, and if you go back you will recollect that this inversion layer was basically Qn, where n was the number of electrons per unit area, which was nothing but Cox into Vg minus Vt, where Vt was the threshold voltage. So, that is the way we defined the number of electrons per unit area, because Cox is per unit area. Now, what we want now is the number of electrons per unit volume, which is given by small n. So, if this is the number of electrons per unit area, what is the number of electrons per unit volume? It is this number divided by the thickness of the channel, which is RH. Okay. So, this is the number of electrons per unit volume at the interface, provided the potential in the semiconductor or this channel potential is 0, because in the case of a MOS capacitor, what is the difference, what is the voltage difference between the metal and the semiconductor? It is Vg minus 0. But now, if I were to take this little section here of length dy, so let us say that is my insulator and that is my semiconductor. The potential here is Vc of y, and the potential drop across the section is dVc. And now my gate metal, okay, so let us look at the section that we are analyzing here. So, we have considered this little section, we have taken the section all the way through. Let us cut this little section all the way through. You have the gate, you have the insulator, you have the semiconductor, the length of the section is dy, the potential drop. So, you have the channel here, the potential drop across this channel is dVc, and therefore, the electric field in that section from here to there is dVc by dy, okay, dVc, let me just write it clearly, dVc by dy, that is the electric field, and this potential of the channel is some Vc of y, because you know it is sitting depending on where the y is, how far are you from the source, depending on what your y is. So, that is the source, and this distance is y, right. So, that is the situation. So, now if you think of it as a MOS capacitor, it is a MOS capacitor, but the semiconductor is not at ground, but it is at some Vc, and therefore, the gate to semiconductor voltage difference is not Vg, but it is Vg minus Vc. So, that difference is, so just to tidy up this place a little, this difference is Vg minus Vc of y, that is the gate to semiconductor. So, what I am going to do is we are going to replace this little term here, instead of saying Vg minus ground, we are going to say it is Vg minus Vc minus Vt into Cox by H is your Q into N. So, we now have this equation here, which says that Q into N, where N is the number of electrons per unit volume, is Cox into Vg minus Vt minus Vc of y by H. And what we are going to do is we are now going to substitute this Qn in this expression for the current. So, we now have IDS, we have taken the WH over to the other side, is Q n mu dVc by dVy. So, that is the current density into WH, that is the area, and Qn is nothing but Cox into Vgs minus Vt minus Vc by H. Okay. So, it is now the potential with respect to the source into mu into dVc by dy into WH, and see the H cancels off, the H was not required. So, even though our assumption on what H is and how we treat H was all arbitrary, we really do not need it, it just served to explain the situation, and therefore, you have this little differential equation that needs to be solved. You have IDS is equal to this particular term. So, you have mu W Cox Vgs minus Vt minus Vc into dVc by dy. So, you take dy to the other side and you solve this differential equation. Okay. So, you integrate y from 0 to L, this is not clear, but this is L. So, as you integrate from 0 to L, what are we doing? We are moving from the source to the drain, and therefore, Vc will vary from 0 to Vds. So, when we did our experiment by moving the voltmeter along the channel, we saw that as we moved from the source to the drain, L varied y varied from 0 to L, and the channel potential varied from 0 to Vds. So, you apply these limits and solve this equation, and you will end up with your current voltage characteristics of the Mosfet. Okay, so, that is the derivation of the simplest model for the current voltage characteristics of the Mosfet. But there are a lot of problems in this. Okay, so, many assumptions made, many implicit assumptions made. So, what is the first assumption that we have made here? The first assumption is the fact that we have actually used this expression for drift velocity. When is this expression valid? This expression is valid only under low electric fields. So, that is the first assumption. We have assumed low electric fields, which implies low Vds or large L, but I will tell you why it implies low Vds in this case. This expression is valid for low Vds because we have made another assumption. We have said that this channel thickness remains H throughout from source to drain. I mean, irrespective of Vc varying a lot, okay, Vc is varying from 0 to Vds, we have said that the channel thickness remains H. Okay. Normally, as we approach, as Vds becomes larger and larger, as Vc becomes larger and larger, you see Qn becomes smaller and smaller. Okay. So, therefore, this channel should actually taper off as we head towards Vds. So, we have made this implicit assumption of low Vds, okay, and we have assumed we have derived the current voltage characteristics for that condition. Okay, now, so this region of operation is something called as linear mode of operation. Okay, so, it is a technical term. So, when we say the Mosfet is operating in linear mode, what it implies is the Vds is very low, and in particular Vds is less than Vgs minus Vt, and I will tell you why. So, why is this a linear model? Clearly this is non-linear, right, you have a Vds square by 2. But if the Vds is very small, the square compared to Vgs, if the Vds is much smaller than Vgs minus Vt, then this term can be ignored and you have only this particular term. So, what you are saying is that you have this device and you have a Vds, which is a voltage across this device, and you have a current that is more or less proportional to Vds, which means that this device despite it being nonlinear, at low VDS it is behaving like a resistor. Okay, you see that is the conductance of this resistor. So, you have IDS is equal to the conductance into VDS, or the inverse of this term is the resistance of the resistor. So, that is why we say it is the linear mode of operation. Okay. Now, what happens if we start increasing VDS? So, this model is great, but it is not really general, because we do not know what happens when you start increasing VDS. Okay. So, when you start increasing VDS, the channel or the thickness, the so called thickness of the channel will not be constant. If my VDS, why is it not constant? So, let us look at two MOS capacitors. Let us take a section here and let us take a section here. Okay. So, let us take, so that is a very wide section. So, let us take a little thin section here and let us take a thin section here. So, what is the MOS capacitor in this region first? So, that is what we used, that is the one we used for all the analysis. You have a gate, insulator, semiconductor. What is the channel potential, or what is the potential here? It is some Vc, and the Vc is approximately 0, and we know that Vg minus Vc is greater than Vt, or in other words, let us say VGS minus Vc is greater than Vt, or in other words VGS minus Vt is greater than Vc, or effectively this gate voltage is strong enough to overcome the channel potential. So, this is large enough, and therefore, it is strong enough to pull electrons near the interface. But what happens if my channel potential becomes larger than VGS minus Vt? So, let us take a situation where you have gate, insulator, semiconductor, but the channel potential is very large. Again, when can this happen? This can happen when the VDS is very large. The channel potential is very large, and now you look at the capacitor, you have Vg. What is the voltage difference between the gate and the semiconductor? It is Vg minus Vc. Now, Vg minus Vc is negative, or it is let us say 0, or in fact we should be looking at the potential above Vt, because we have to cross Vt to get this. So, when you have the condition of VGS minus Vt being less than the channel potential, you cannot have an inversion layer, there are no electrons there, and therefore, as we start heading towards the drain, the channel should actually taper off, and the moment VGS becomes VGS minus Vt becomes equal to VDS, that is when the channel potential becomes equal to the channel potential, becomes equal to the channel potential, this thing there should be no more electrons, and the channel would simply taper off, it would taper off. Okay, you will not see electrons there anymore. And this point where the channel tapers off is called as the pinch off point. Okay, it is a technical term, it is called pinch off. Okay, so I do not know if I was clear enough, so I am going to repeat this concept. So, the point where, so we have a channel, you have got a drain, you have got a source, and you have got a channel potential that is varying from source to drain. Now, the drain voltage is very high, there is a possibility the channel potential is very large, particularly near the drain side, whereas the channel potential is close to 0 near the source side. So, you will have VGS being greater than VGS minus Vt being greater than Vc near the source side. So, you will have electrons there, but there will be a point where the Vc becomes equal to VGS minus Vt. So, let us say that happens at some location where Vc becomes equal to VGS minus Vt, and as you move between that location and the drain, the Vc is always going to be greater than VGS minus Vt. So, throughout that region you cannot have an inversion, and the channel is said to be pinched off. So, you have electrons here, but suddenly beyond this pinch off point, beyond this point there are no electrons, because inversion has not happened. Okay. Now, let us do this experiment, this thought experiment. Let us say we are running the transistor in linear operation, in linear mode of operation. That means the VDS was very low, and we now start tweaking up the VDS, we start increasing the drain to source voltage. The drain to source voltage at which, so as you are increasing the drain to source voltage, the channel potential is increasing. So, let us watch the channel potential near the drain, let us only focus on this section here. So, this channel potential is increasing as you increase the drain to source voltage, it is in fact equal to VDS, right. So, the drain voltage at which the channel potential becomes equal to VGS minus VT, or that particular drain voltage is given a special symbol, it is called the VD sat, and I will tell you what that is. At that particular drain voltage, the channel is just pinched off near the drain end. Okay. There are electrons, every other region is inverted, but just this end near the drain is, you do not find electrons, because the VGS minus VT is now no longer greater than the channel potential. Your VGS minus VT minus channel potential has become equal to 0, and therefore, Qn has become equal to 0. So, this end is now pinched off, okay, and we say that the transistor has gone away from linear mode of operation, because now our model is no longer valid. It has gone away from linear mode operation and it has entered something called as saturation mode operation. And now, if we keep increasing VDS further, the transistor will continue to remain in saturation mode operation. Okay. Now, in saturation mode operation, so what saturates? We find that the current through the transistor saturates, and I will explain what happens. So, you think of this channel as a resistor, this entire region between source and drain as a resistor. So, let us say we have hit the pinch off. Okay. So, the drain is sitting there, the source is sitting here, and there were electrons all the way till this point, but then the channel potential at this point is now greater than VGS minus VT, and therefore, this region is all pinched off. All this is the pinch off point, and there is no electrons from here all the way till the drain. So, let us imagine this to be a large resistor between source and drain. So, how would what would the resistance look like? You have a lot of electrons from the source to the pinch off point. I am sorry, I have run out of space, there is a lot of explanation here, but there is not much space for me to write anything. So, do bear with me. So, let us say you have this as a resistor, you have electrons all the way and then you hit the pinch off point, and beyond this you have a large resistor, because you do not have an electron channel anymore. So, now when you have a drain to source voltage, most of the voltage drops across the large resistor in the region that is actually depleted. All this region is now depleted, the region beyond the pinch off point is all depleted, right. So, you have a large resistor here, and you have a much smaller resistor here. So, you have most of the voltage drop across this region. So, what happens to the electron current? You have a large number of electrons. So, Qn is good, it is larger, and then Qn becomes 0 beyond this point. So, you have a large number of electrons. Look at the electron traffic. You have a large number of electrons moving at low electric field all the way till the pinch off point, and then after that the electric field is very large, but there are not many electrons. So, you have a few electrons that are shooting past, that are racing past this depleted region, that are racing past this region because of the high electric field. So, you have fast electrons and you have slow but larger number of electrons. Okay. So, that is what is going on. So, you have slow electrons, but a large number of them. So, which means that the entire flux has got low velocity, but large number. Beyond this, the number becomes very small, but the velocity becomes very large. So, nevertheless, the current is maintained, but the current does not increase very significantly if you increase VDS, okay, because it is not a, it is a non-linear device now in some sense. Okay. So, the VDS does not impact current beyond the pinch off operation, and therefore, the current has increased all the way in the linear mode. In the linear region, the current kept increasing, but then after that the VDS stopped impacting the current. So, we say that the current has saturated, the current is not going to be impacted by the VDS anymore. And what is the equation for saturation? We simply say that the moment this point is pinched off, the current is the same as the last value of the linear current. Okay, so, which is what? Which is when VDS becomes equal to VGS minus VT, or in other words, when the channel potential at this location becomes equal to VGS minus VT, then the device current becomes constant, it stalls, it does not increase anymore with VT. So, what we do is we take this equation, which is the linear equation, and we substitute, in order to find out what this current is, we just substitute, we look at the last point on the linear region, we substitute VDS is equal to VGS minus VT, and we use that as the current for all values of VDS which are greater than VGS minus VT. Okay. So, we just say when VDS is VGS minus VT, what happens? The current becomes VGS minus VT square by